on what's new in Pointwise version 17.2. My name is Carolyn Weber. I'm the manager of the technical support group here at Pointwise. Eric Gant is an engineering specialist in the same group and will be answering your questions after the webinar. So today we're going to be talking about this list of new features in Pointwise version 17.2. As you can see, we have a couple of features that deal with how we treat structured domains in T-Rex blocks and how you can get unstructured hexahedra from those. We also have a new feature that deals with how you can create unstructured blocks with multiple faces automatically. In addition, we have some productivity features related to setting light sources and automatically mirroring symmetry grids on export. And finally, we have some new CAE solvers that we'd like to introduce to you, and we have some upgrades to our CAE support that we'll talk about. So let's go ahead and get started and look at how we're using structured domains in T-Rex meshes. In the past, when we had structured domains that users grew T-Rex boundary layer meshes off of, what we would do is we would create a base pyramid on each quadrilateral cell. On that base pyramid, we would then place anisotropic tetrahedra, and we would use the T-Rex algorithm to march those anisotets off that into a boundary layer mesh. When you exported this type of mesh from Pointwise to your CAE solver, what you would get would be a base pyramid, a few anisotets, and then layers of prism cells above that. Ideally, what we'd really like to see is you get hexahedra instead, and that's what we've done with version 17.2. So now with 17.2, we are still placing a base pyramid on that quadrilateral cell, but we're adding something a little bit else. So now we create a base pyramid on each quad, and we create that base pyramid at the height that you have specified for your wall spacing. Then we place 4 side pyramids on each base pyramid. These 5 pyramids effectively form the first layer of T-Rex cells. These are also the 5 cells that will be combined into a hexahedral cell when you export your mesh from Pointwise. Now once you move past the first layer of T-Rex cells, what we do is we take the triangles that are exposed on those 4 side pyramids and we march those out into anisotropic tetrahedra using the T-Rex algorithm. Now, I know some of you are aware of this, but for each stack of 3 anisotetrahedra, we can form 1 prism. So you can visualize for these stacks of anisotets that we're growing off those side pyramids that we effectively can get 4 prisms per layer, which can then be combined into 1 hex per layer. So on the base level, we're going to have 5 pyramids that are created into 1 hex on export, and above that, all those anisotets will be combined into hexahedra. So let's go ahead and look at how this would work with a real case. So what you see here is an intake port and valve geometry and surface mesh that I've created in Pointwise version 17.2. If you look at it, you'll see that a majority of it is structured, but I have chosen in areas that can be difficult to find a good topology for, I've chosen to place unstructured domains instead. This is just to make my life a little bit easier in handling this complex region. Now, if we look at the remainder of this surface mesh, you'll notice that on the bottom, I've chosen to also place structured surface mesh. I'd like to grow a boundary layer mesh off of all of these surface domains except those at the inlet, which is over here. So I'm growing a boundary layer mesh off the bottom of this cylinder. Since I want hexahedra, for me the best topology is an OH topology, which we also call a butterfly topology. Now, as I move around, I'm going to come over here and look at the inlet. Now, these domains at the inlet, like I said, are the only ones where we are not going to be growing a boundary layer mesh. Instead, for these domains, as we grow boundary layer mesh inwards from these purple cylindrical domains, I want that boundary layer mesh to match the growth rate in the cells you see here on these structured domains exactly. That's great. We can now do that with version 17.2 for Pointwise. But before we go into setting up T-Rex for this, we first need to get a little bit more information about these structured domains. Namely, because they were created via extrusion, and then I used the grid solver to smooth them, the growth rate on these structured domains is not a constant. It varies as we march out from the wall. So what I need to do is select these structured domains, take them into examine, and see what my average growth rate is for the inlet domains. I then can use that average growth rate when I'm setting up my T-Rex block as my volume growth rate. So let's go over here and turn on the domain selection mask. And I'm going to select these 4 structured domains that ring the inlet. This is where my boundary layer will exist inside the volume. And I'm going to come over here to examine, and I'm going to come down to length ratio J. So the length ratio J diagnostic essentially looks at the edge length ratios between adjacent cells in the J computational direction. So for me, the J computational direction is that is normal to the cylindrical walls. So if I select this and I come over here and zoom in on these domains, you can see that as I move my cursor over the domains, the probe will show you the adjacent cells that it's measuring the edge length ratio of. This is effectively the local growth rate for this domain, or for this area of this domain. So I can look at this and I could try to eyeball it and come up with an average, but it's way easier to let Pointwise do that for me. So I'm going to come over to Examine, and in Examine I'm going to click on the Extrema tab. And in this tab we display the maximum value for each diagnostic function, the minimum value, their location. We also display an average value. So for these inlet domains, my average length ratio in the J direction is 1.18, which is effectively the average growth rate for these domains. This is what I'm going to use when I set up my T-Rex block. So let's go ahead and click Close. And now I want to zoom out. I'm going to use F2 to fit to screen. And what I want to do is I want to select all of my domains. I want to come over here and make sure my grid type is set to unstructured. And then I want to move over to the Assemble Blocks command on the toolbar and select it. This creates one block out of all the domains I selected. So now I can turn on my block selection mask, pick the block, and come over to Grid and T-Rex. In the T-Rex panel, there's really only a couple of settings that we're going to use. The first one is the max layer setting. The max layer setting essentially specifies the upper bound for your T-Rex mesh. The number of layers you specify here is where T-Rex is going to cut off the growth of cells. Now, for most meshes, including this one, I try to set this to a high value because I want T-Rex to grow as far out as it can. It'll essentially stop once the cells it's growing hit isotropy, encounter a collision, or violate some quality criteria. So I want it to reach those. For this case, because of this small cylinder I have here near the inlet, I think 40 is going to be a large number for our boundary layer mesh. So I'm going to enter 40 for our max layers. The next thing that I want to set is the number of full layers. For this particular application, I need to have one complete layer of prisms and hexes adjacent to the wall in my boundary layer mesh. Because of that, I need to make sure that Pointwise gives me this complete layer as it's growing the boundary layer mesh. If I leave it at 0, that tells Pointwise that if it needs to, it can immediately stop growing T-Rex cells off the surface mesh on the very first layer. I want at least one layer, so I'm going to set that to 1. If I needed to have at least 5 or 10 layers, I could also set it to those. Now for growth rate, we went and found out what our growth rate should be for our volume. I need to uncheck Use Default and change this to 1.18. Now next, I'm looking at push attributes. The only domains I have in this mesh that I want to match my boundary layer are those structured domains at the inlet that we've already talked about. When we use push attributes, it's typically used on unstructured domains that are set to a match condition. So since we only have structured domains here, we're going to leave this unchecked. Now the last thing that you want to set in the T-Rex panel is under the advanced frame. So I'm going to check that to expand it, and that's the collision buffer. If I zoom in here, you can see that inside the intake port I have this valve that comes down into the large cylindrical volume. This valve is actually quite close to the neck of the intake port in several areas. You can see all through here it's very close. This gap region is going to be growing a boundary layer mesh off the intake port inwards and then off the valve outwards. So you know there's going to be a collision in this gap region. I'd like to make sure there's enough space between these two boundary layer meshes that are growing together for me to insert a tetrahedral cell that is not squashed or flat. So what I'm going to do is I'm going to come down here to the collision buffer setting. I'm going to uncheck Use Default, and I'm going to set this to a value of 2.0. For gap regions, I find this to be a great value to use for most T-Rex meshes. Now we need to set up boundary layers, or boundary conditions. So in the Boundary Conditions tab, you see that right now I only have one boundary condition, and that is unspecified. It contains all the domains in my mesh currently. To set up my boundary layer, I need to have a boundary condition that specifies a wall spacing and a wall type. So click on New, and then come up here where it says BC-2 and double click, and let's call this intake port. Now for the type, like I said, if I set it to wall, that means that I'm growing a boundary layer mesh off of it. So I select wall, and that gives me the option to specify a wall spacing in this delta S column. So let's double click on 0.1, and my wall spacing for this particular application is going to be 0.01. Press enter. And now all we have to do is select the domains that should go into this boundary condition and apply them. So I'm going to hit F2 again to reset my view. And what I want to do is I want to select all the domains except for the inlet domains right here. I can do this very easily by just using a selection box that includes everything but those inlet domains. Once the domains are selected, I can move over to the Set checkbox for intake port and check it, and that moves those 19 domains into that boundary condition. Now our next boundary condition needs to be a match type boundary condition to tell Pointwise which domains it should match the boundary layer to. So go down here and click on New and move back up to where it says BC-3 and double click. I'm going to call this inlet because we're only putting inlet domains in here for a match condition. For type, I'm going to double click and call this match. Now, there's two ways I could apply these domains to the boundary condition. I could come over here and select them individually and apply them to the boundary condition, or I could come up here where they sit in the unspecified boundary condition, and I could select that boundary condition, then move down and click on Add to Selection. Now they're selected. I can come up and click on the inlet boundary condition. So now all my domains are applied to boundary conditions for T-Rex, so it knows how to grow off of certain cells. I can move over to the Solve tab and click Initialize to begin growing my volume mesh. Now, as it grows, I'm going to expand this panel just a little bit so we can see a little bit more feedback. So you have this white front that is growing into the interior of the intake port. This is your boundary layer mesh that's growing. As it grows inwards, you'll have cells start to stop because of isotropy or collisions. Those cells you'll see show up in red in this front. Eventually, the entire front will be red because they have all stopped, and this is to be expected. Once that happens, that front will be passed off to our isotropic tet mesher, which will fill the remainder of the volume with isotropic tets. At that point, initialization will be finished. Now, you can see here that I have 17 complete layers that were generated and 20 total layers. So past layer 17, we're generating incomplete layers. That means that layer 17, that was where we had the first cell stop due to a collision or isotropy. And it looks like they started up here where the intake valve and the intake port are very close together. Okay, our front is almost finished growing. All right, now it's working the isotropic tet mesher. And our mesh is finished. So we got a total of 34 layers, 17 of which are complete, and the total mesh size is 3.7 million cells. So right now we have our anisotropic tets and pyramids. So let's go ahead and click OK to save the block in its initialized state. And our next step is to create the unstructured hexahedra and the prisms. We do that by selecting the block. It's already selected. And then going to File, Export, and CAE. Now, I'm going to choose this file that I've already created, intake port, export. I'm going to click Save. You could enter your own file name there. And now I get to the Export CAE panel. This can look different depending on which solver you're in, but any solver that supports cell combination will have this option. So the option is called Combine Anisotropic Tetrahedra. When this is activated, on export, Pointwise looks at all the cells grown off of unstructured domains and combines those into prisms. It then looks at all the cells that were grown off of structured domains and combines those pyramids and anisotets into hexahedra. So if I click OK, Pointwise will go off and it will start combining all these cells as it exports them. And when it's finished, down here in the Messages window, it will give us a readout of how many cells of which type were created. Now, you can see here in the progress bar, we're almost done. Okay, now here are cell counts. Out of this mesh that was, let's see, 3.7 million cells, we have now 200,000 hexahedra, almost 300,000 prisms, 38,000 pyramids, and roughly 230,000 tetrahedra. The total mesh size with cells combined is 780,000 cells. So if you compare this to the mesh when it was just anisotets and pyramids, that's a cell count reduction of 79 to 80%, which is significant. In addition, your boundary layer mesh also has higher quality cells now. We have prisms and hexes. Now at this point, to see these prisms and hexes, what you'd want to do is take this exported file and read it into your favorite solver or post-processor and take a look at what the cells look like. So for us, I took this mesh and I read it into Insight, and I took this snapshot so you could get an idea of what they look like. In this image, the orange cells that you see displayed here are prisms that were grown off of the unstructured domains. The white cells are hexahedra that were grown off of the structured domains. And then you can see a thin layer of green cells here. These are the pyramids that are used as interface cells between the hexahedra and the isotropic tets seen in blue. Now, this is the type of mesh you would get, and I went through this demonstration a little quickly. So if you would like to try this out for yourself, try creating these structured and unstructured surface domains, setting up the T-Rex volume and creating it, and exporting it to your own solver. You can do that using our new tutorial called the Intake Port and Valve. This is packaged with version 17.2. You can access it by going to Help Tutorial Workbook. This will demonstrate how to make those hex cells in your boundary layer mesh, as well as how to set up those structured domains as T-Rex match boundary conditions. So now that we've talked about structured domains and how they interface with T-Rex, let's go ahead and look at some of our other features. The next feature that I think is really significant is the ability to create unstructured blocks automatically with multiple faces. In the past, this could be a somewhat tedious process in Pointwise, so we've tried to really speed it up for you. So this command is available in the Create Assemble Special Blocks panel. There's a new tab there called Automatic. And once you click on this tab, Pointwise puts you into a mode where it expects you to select all the domains that you want it to consider for your new block. This could be the domains for the outer face and any inner faces. Once you've selected those, you choose what options you want to use for creating the block. Do you want Pointwise to create baffle faces if it finds a domain floating in space in the interior of your block? Do you want it to create interior blocks? This means that if it creates an interior face for your block, do you want it to create a block within that interior face that you can mesh as well? You select your options, click on Assemble Faces, and Pointwise will go off and create your block. So let's go ahead and look at this on an example that we're all familiar with. Okay, so what you see here is the wing pylon store case from our T-Rex tutorial that's in our tutorial workbook. Now for this case, we have an outer face that's a hemisphere and a symmetry domain that is attached to a wing. Underneath the wing is a pylon, and underneath the pylon is a store that is separated in space from the pylon, so there's no attachment there. Now, this store would be an inner face for the block. Additionally, behind the wing is a baffle domain that would also be an additional face for the block. In the past, I would have to create this block by selecting a domain on the wing, then selecting all the adjacent domains and saving that face. Next, I would have to select one domain on the store, select all the adjacent domains, and then save that face, and keep doing this until I had all the faces saved for my block. With our new command, we don't have to do that anymore. So let's go ahead and look at that. So let's go to Create, Assemble Special, Block. All right, click on the Automatic tab, and while you're in the Automatic tab, select all the domains. Now for us, we want to create a baffle face behind the wing, so I'm going to check that option on. I do not want to create an interior block. In this particular instance, what that would mean is it's already going to create an interior face for that store. I don't want to mesh the inside of the store, so I'm going to leave this unchecked. I'm going to click Assemble Faces. And now Pointwise has created my block with the wing and the hemisphere and the symmetry domain in one face. The store is a separate face, and so is the baffle domain behind the wing. And you can see that reported here in the table. So if you're happy with this, you would click OK to save the block. If a face was created that you did not want to keep in the block, you could click on Begin Removing Faces, deselect it, and then save your block. So let's go ahead and click on OK, and now our block is saved. So our next feature, I think, is really helpful if you're trying to take a picture for a report, and it's our shading light source tool. So we now give you the capability of changing the direction of your light source when you have shaded domains or database surfaces. Now, you can set the light source so that it's fixed to your view or so that it's fixed to the scene or the model. Once you're in this command, you're going to want to use the Control left mouse button to change the direction of your lighting source. Or if you know a specific vector that you want your lighting source to run along, you can also set that within the advanced frame. So let's go ahead and look at this case with that command. So it's under View, Set Lighting. So by default, you're put into a mode where the lighting source direction is set with your viewer. So that means I'm going to set the source, and no matter how I move my model, the lighting direction is always going to stay set with my view. So you're going to see the shading change on the model as I move it. So I'm going to hit Control left mouse button, and you can see as I move my cursor that this arrow changes the direction of the light source. So I'm going to fix it here where it's going right down on the wing. Now as I move my model, you can see that the light source is always in that direction, straight down. If we change it to a scene, I can either align it with my current view, or I can use Control left mouse button to set it explicitly. Now, I'm setting it to the top of the wing again. Now, if I move my model, you'll find the shading does not move anymore. It stays fixed to the top of the wing. So the bottom of the wing should be very dark. And it is. Now, last but not least, if you want to, you can come to this advanced frame. And here's where you can set your vector explicitly for your light direction if you know it. Now, this is a feature that we've had people asking for a little while, so I think it's going to be very popular. This allows you to mirror symmetry grids on export automatically. So you can right now in Pointwise copy and paste your grid and then mirror it about a plane and get a complete full configuration. However, a lot of people, they don't want to do that. They'd really like that just to happen automatically as the grid's being exported. It's a lot less to deal with in Pointwise. So you can do that, and you actually need to use a two-step process to do it. The first step in the process is to set your mirror plane, and you do that in the CAE menu. The second step is in File Export CAE, telling Pointwise that you do want to mirror on export. So let's go ahead and look at that with the real case. So in this instance, I'm going to zoom out so we can see the entire mesh. You can see it's a symmetry grid about y equals 0. So I'm going to go to CAE and set mirror plane. So this is the first step in the process. Now a panel appears and it gives you several options for how you set the mirror plane. You can use point normal, 3 points, a constant x, y, or z, or the plane coefficients. You can also select an existing database plane if you have one available. Now in this case, it defaulted to constant x, y, or z and an x equals 0 plane, which is not appropriate for this case. So I'm going to select y equals 0, and you can see that the preview switches to the y equals 0 symmetry plane. So this is what your mirrored grid would look like if you exported it right now. So check to make sure that's what you want, and if it is, click on OK. Now before I leave this panel, if you ever decide that you don't want to mirror your grid on export anymore, you can always come back into this panel and choose Undefined, which will unset the mirroring. So let's click OK to proceed as is. Now to export this and have it mirrored, I just need to select the block and go to File, Export, CAE. I'm going to enter a name. And in the panel here, you can see the option that I pointed out before, Mirror on Export. When I check this, that tells Pointwise to mirror the entire grid on export, and it will also show a preview of the mirrored grid once again. You click OK, and Pointwise goes ahead and exports the entire grid. Now, our next productivity enhancement has to do with draw curves. And I know this seems like a very small feature, but the draw curves command is used heavily in Pointwise to create both database and grid curves. So we wanted to give you easy and quick access to all the different curve types. So if you select the pull down that we've now added to the Draw Curves toolbar button, you'll find that you now have direct access to all these curve types. So I'm in Pointwise, and there's my Draw Curve pull down. I have access to line curve, line on database, all the options directly here from the toolbar. The great thing about it is once I select one, let's say I pick a pole, I'm going to create a pole out here in space and click OK. The pole now becomes my default curve option on the panel. So it always uses whatever the last curve type you used as the option if you just click directly on it. This is hopefully to help you quickly create a bunch of poles or conics or circles. Now our last group of features that are new in Pointwise version 17.2 have to do with export. One of the biggest ones is CGNS. We've upgraded our CGNS export so that it now supports version 3.1.4. Now what this gives you are some new data options. You can now export structured blocks as unstructured hexahedra. You can now choose to include parent elements when you write out your CGNS file. This means that your elements, which are the faces of your cells in 3D, are written out to element_t nodes. So this tells the CGNS writer what cell ID that element or face belongs to. You can choose to include your donor information, which essentially writes the donor connectivity information to the zone grid connectivity_t nodes. You can also choose, if you have unstructured and hybrid blocks in your mesh, how to handle the grid interfaces. So you can choose to have the interfaces communicate on a face-to-face, a node-to-node, or a cell-to-cell level. Moving on, we now support 3 new CAE solvers additionally. We support Fun3D, SC Tetra version 9, and Gambit neutral file format. And last but not least, our Nastran export has recently been updated to support C pentas, which are pyramids. So that's all of our new features for Pointwise version 17.2. So at this point, I'd like to pass it off to Eric Gant to answer any questions you might have about these new features.
Thank you, Carolyn. So we actually have had a few questions during the presentation already, so I'm going to reiterate those questions for everyone who's present, and of course if anyone has any additional questions at this time, please go ahead and type them into your question box that you have available in GoToWebinar. So the first question that I got has to do with the collision buffer setting for the attributes for T-Rex when it's marching, and specifically what units is the collision buffer in. So that number that you type into that field is actually a factor that is applied to the current cell height at the current T-Rex layer. So basically what you're telling it is how thick you want that collision buffer to be based on the current cell height. So the default, which is 0.5, is basically saying on each of the layers I want to have at least a half a cell height buffer area. So when Carolyn changed that to be 2, that means that for each side of the colliding layers, she wants to have at least 2 cell heights available, which gives more breathing room between the layers to be able to generate those isotropic tetrahedra. So that was a very good question. The next question that I received has to do with the pyramid aspect ratio attribute, which is in the unstructured solver in the main attributes tab. And does that particular setting have any effect on T-Rex in the T-Rex method? And the answer to that is no. That setting actually is only applied to pyramids that are used in isotropic only blocks, so those that are only being initialized isotropically. Otherwise, any of the pyramids that you see in a T-Rex block that Carolyn has demonstrated for you, whether they are on one of the surface boundaries or somewhere in the interior, those cells are entirely controlled by growth rate and quality controls and other attributes that are specified for T-Rex. So that was also a very good question. The third question that we received has to do with the new mirror at export command, and specifically, is the old symmetry domains prior to mirroring, are those automatically set up and treated as connections after the mirror at export? And the answer to that is yes, they should be combined automatically at export and become a connection automatically in that grid when it's exported out. Now, of course, there could be a caveat to that. If for some reason you have a domain that is not truly in that symmetry plane, then you could end up with a situation where a couple of domains after mirror have not been combined into a connection automatically. So that would be something to be careful of. Okay, so let's see. It looks like we may have a couple of additional questions. Can you use the push attributes option for structured domains that are on the boundary if you want to? You can use that option if you want to and try to have it force qualities from the T-Rex grid onto the structured domain. The code is set up so that it will not allow you to do that if a structured domain is an interface with a structured block, because that would destroy the structured block that's adjacent to the T-Rex block. However, if it is not, you can use the push attributes to try to update that structured domain. And actually, it looks like that was our last question that I have in the list here. So
actually, Eric, we got one more question. It came in through chat.
Okay.
I wanted to mention it. Ben is asking if T-Rex can create hexahedral boundary layer cells on unstructured triangular surfaces. In other words, would T-Rex push quads down to a triangular surface mesh and override the triangles, which is an excellent question. Right now, T-Rex cannot do that, but that is actually a feature we're considering for a future release. We think that would be very powerful as a next step for the T-Rex mesher. So if anybody else is interested in that, please, email support and let us know so we can add your name to that request.
Okay, there's actually another question here too in the questions field, Carolyn, that I'll cover real quick, and that is, can I display the combined result of the T-Rex grid? That's a good question as well. It comes up pretty frequently. Unfortunately, right now we do not have the ability to display combined cells within Pointwise, and that was part of the reason Carolyn showed it separately in her slide. Main reason for that is that the way we set up our blocking structures originally in Pointwise was so that the cell types would be homogeneous in the different block types, with the exception of an unstructured block being able to contain pyramids on the boundaries only. We are actually laying the groundwork right now for a new major version in the future, which is going to expand our blocking structure to include all cell types. And at that point, we'll be able to open up the combined results of a T-Rex grid internally in Pointwise to examine and all the other features and capabilities that we have in the code. So that's also a very good question. And it looks like that's the end of the questions that we have for this morning. So with that, I would like to point everyone to the last remaining slide that Carolyn has up for display here for you, and the things that are on there. First of all, we will have this recorded webinar available to you to view again or to pass on to someone else, a colleague that may wish to see this webinar after the fact. So there's a URL there, our website /webinar, that you can access that. Of course, if you ever have any questions about this or anything else related to the code, please do let us know. You can email us at webinar@pointwise.com and support@pointwise.com. And then finally, at the bottom of the slide is a save the date. We are having our next user group meeting this fall in October in Anaheim, California. It's very exciting, and we hope that many of you can attend, and also, if possible, be a presenter at our user group meeting. We do have the call for papers open now, and there is a URL there on the slide that you can access to get more information about the call for papers and about the UGM in general. So that's it for our webinar this morning. Thank you very much, all of you, for attending and spending a half hour or so with us to learn a little bit more about our latest features. Thank you.